25 microseconds. That is how long it took. A microsecond is 1/1,000,000th of a second. 25 of them is roughly 1,000 times shorter than the blink of an eye. It is shorter than the time it takes a single nerve signal to travel 1 centimeter along your arm. In that window, a machine sitting in a laboratory in Hefei, China, produced one answer to one mathematical problem. Now here is the other number. The most powerful supercomputer on Earth, running the best classical algorithm anyone has written for that same problem, would need more than 10 to the 42nd power years to produce the same answer. That is a 1 followed by 42 zeros, years. Let me try to make that number mean something, because on its own it is just a smear of digits. The universe is about 13.8 billion years old. If you took the entire history of everything, from the Big Bang to this moment, and you ran it end to end, then started it over, and did that 100 billion times, you would still not be close. You would need to repeat the entire lifespan of the universe, roughly 10 to the 32nd power times. That is the gap. 25 microseconds against a span of time so long the concept stops functioning. The machine is called Jiuzhang 4.0. The results were published in the journal Nature in May of 2026, and it does not run on electricity flowing through silicon. It runs on light. Now, I want to be direct with you about something up front, because this is where almost every video about this story goes wrong. That comparison I just gave you is real, it is peer-reviewed, and it is also, in a very specific sense, a magic trick. Not a fraud, a magic trick. There is a reason the problem was chosen, and once you understand that reason, the whole thing becomes far more interesting than the headline, not less. So over the next 20 minutes, I am going to walk you through 3 things. What this machine actually did, why the number is simultaneously true and misleading, and what it genuinely tells us about where China now sits in a technology race that most people have not been paying attention to at all. If you like stories where the engineering and the geopolitics turn out to be the same story, hit like and subscribe, because that is what this channel does every week. Let us start with the problem itself, because everything depends on understanding it. The test that was designed to be useless. The task is called Gaussian boson sampling. That name tells you nothing, so forget it immediately. Here is what it actually is. Imagine a machine, roughly the size of a large room, that is essentially an enormous maze made of mirrors, crystals, and beam splitters. You fire particles of light into one end. Those particles bounce, split, recombine, and interfere with one another as they travel through thousands of possible paths. At the far end, you have detectors that record where each particle came out. Run it once, you get a pattern. Run it again, you get a different pattern. The patterns are random, but they are not evenly random. Some patterns come up far more often than others, and which ones depends on the exact configuration of the maze. The task is simply this: produce a big pile of those patterns, matching the statistical distribution that the physics dictates. For the machine, this is not really computation in any familiar sense. The light does not calculate anything. It just goes through the maze and comes out. The answer is a physical consequence of the apparatus. The way water finding its level is a consequence of gravity rather than a calculation about gravity. For a classical computer, it is a nightmare. To predict that distribution, a normal computer has to consider every possible path every particle could have taken and account for how all of those paths interfere with each other. The number of possibilities does not grow steadily as you add photons. It explodes. Add one more particle of light and you have not made the problem slightly harder. You may have doubled it, or worse. This is the crucial thing to understand. Gaussian boson sampling was not chosen because it is useful. It was chosen precisely because it is the kind of problem that punishes classical computers as brutally as possible while being almost trivially easy for a light-based apparatus to just physically do. It is a stress test, not an application. Think of it like this. If you wanted to prove that a bird was better than a car, you would not race them down a highway. You would pick a route with a canyon in the middle. The bird is not generally superior to the car. It is superior on this deliberately chosen route. Nobody in the field pretends otherwise. The physicists who built this machine say so in the paper, and knowing that does not diminish what follows, because the engineering required to fly across that canyon is extraordinary, And it is exactly the engineering that matters for everything that comes after. The problem that killed everyone else. To appreciate what the Chinese team actually solved, you need to understand why light-based quantum computing had been stuck for years. The idea of using photons is old, and it is attractive for good reasons. Photons move at the speed of light, obviously. They do not interact much with their surroundings, so they are resistant to the environmental noise that plagues other approaches. And unlike superconducting quantum computers, which have to be chilled to within a fraction of a degree of absolute zero inside enormous refrigerators, photonic systems can operate at much more forgiving temperatures. So why did photonics spend 2 decades as the underdog? One word: loss. Every time a photon passes through a piece of glass, bounces off a mirror, or travels down a fiber, there is a chance it simply gets absorbed and vanishes, not corrupted. Gone. And there is no way to make a copy of a quantum state to replace it. That is not an engineering limitation. It is a law of physics. Now do the arithmetic on that. Suppose each component in your optical path preserves 99% of the light. That sounds superb. But if a photon has to pass through 100 components, 99% survival at each step leaves you with about 36% overall. Push to 1,000 components and you are down to a fraction of a percent. And you do not need one photon to survive. You need thousands of them to survive simultaneously, in the same run, all still carrying their quantum relationships intact. This is why the earlier generations of these machines topped out where they did. The first Jiuzhang, in 2020, worked with 76 photon detections. Jiuzhang 3.0, in 2023, reached 255. Every additional photon was a fight against an exponential wall of loss. 255 was already a world record. It was also, plainly, a ceiling, what they actually built. Jiuzhang 4.0 detects up to 3,050 photons, not 260, not 400, more than 10 times the previous record, in a domain where every single additional photon had historically been a serious achievement. That did not come from a clever algorithm. It came from a grinding, unglamorous assault on the loss problem from several directions at once. First, the light source. The team built a new kind of optical source producing what is called squeezed light, a state of light with its quantum uncertainty deliberately reshaped and pushed its efficiency to 92%. That means when the machine tries to generate the quantum state it needs, it succeeds more than 9 times in 10. Earlier systems were substantially worse, and every failure at the source compounds through everything downstream. Second, the architecture. Rather than laying out every optical path in physical space, which means more components and therefore more loss, the team used a hybrid design that encodes information across both space and time. Photons are separated not only by which path they travel, but by when they arrive. This lets you build a far more complex interference network without a proportional increase in physical hardware. The final system ran 1,024 squeezed light inputs through a network of 8,176 modes. Third, the detectors. They used superconducting nanowire single photon detectors operating at around 93% efficiency. When a photon does make it all the way through, it gets seen. Stack all of that together, and the overall efficiency of the full system reached about 51%. Read that again, because on paper it sounds unimpressive. Roughly half the light is still lost. But in this field, an end-to-end efficiency above 50% across a system of that complexity is the difference between a demonstration and a dead end. It is the threshold that turns an exponential wall into a slope you can climb. And the team did something that deserves specific credit, which I will come back to shortly. They tested their results against the classical simulation methods designed to defeat exactly this kind of claim, including techniques built specifically to exploit photon loss as a weakness. Now the fight back. Everything I have described so far is what the Chinese team achieved. Here is the other half of the story, and it is the half that almost never makes it into coverage. There is a quiet war going on in this field, and it has been running for 7 years. It started in 2019, when Google announced that its Sycamore processor had performed a task in 200 seconds that would take the best supercomputer 10,000 years. Enormous headlines, genuine milestone, and then classical computer scientists went to work on it. Over the following years, A series of teams developed new simulation techniques, mostly based on a mathematical approach called tensor networks, that chipped that 10,000-year figure down relentlessly. 10,000 years became years. Years became weeks. Weeks became days. One team eventually ran the equivalent computation on a cluster of graphics processors and reported doing it faster than the quantum machine had, with a better fidelity score. The 10,000-year claim did not survive. It was not fraudulent. It was simply an estimate based on the best classical algorithm known in 2019, and better algorithms arrived. And this keeps happening. In May of 2026, researchers at the Flatiron Institute published work in Science using a new three-dimensional tensor network method that pushed back against a prominent quantum simulation claim from D-Wave. In April, a group demonstrated that a set of circuits used in another quantum advantage claim, running on a trapped ion machine, could be efficiently simulated classically after all. And in July of this year, a preprint appeared, arguing that a certain class of these sampling benchmarks may be beatable by a classical sampling method entirely, on the grounds that the genuinely hard part is not producing the distribution, but identifying which specific circuit produced it. That last one is contested, and will be argued over for a long time. That is how the field works. But the pattern is unmistakable. Quantum advantage claims are not permanent trophies. They are challenges issued to classical computer scientists, and classical computer scientists have a strong record of eventually meeting them. So the honest framing of Jiuzhang 4.0 is not China has proven quantum computers beat supercomputers forever. The honest framing is this: China has issued the largest and best defended challenge yet, on a benchmark chosen to favor its hardware, and validated it against every classical attack the authors could find. Whether it survives the next 5 years of classical algorithm development is a genuinely open question, and the researchers involved understand that better than anyone. What it does not mean. Let me clear away the two claims that always attach themselves to stories like this, because both are wrong. The first is encryption. You will see headlines suggesting this brings us closer to quantum computers cracking the cryptography that secures banking and messaging. It does not. Not even slightly. Breaking modern encryption requires a very specific thing. It requires running a particular algorithm, Shor's algorithm, on a machine with a large number of error-corrected logical qubits, meaning qubits stabilized against noise by grouping many physical ones together. Current estimates put the requirement in the range of millions of physical qubits arranged in exactly the right architecture. Jiuzhang is not that kind of machine, and it is not on a path to becoming that kind of machine without a fundamental redesign. It cannot run Shor's algorithm. It cannot run any algorithm you specify. It performs one type of sampling task, and it does that task magnificently. A specialist in this exact question put it plainly after the paper came out. For cryptographic timelines, this result changes nothing. The second claim is that this means China has built a working quantum computer that does useful work. Also no, nobody has. Not Google, not IBM, not UST, not anyone. The entire field is still in the phase of proving that quantum systems can do anything a classical computer cannot, and the answers to genuinely useful problems remain some years out at minimum. If a video tells you this machine is going to design drugs or break your bank account next year, close the video. So why should you care at all? Two reasons, and they are both bigger than the headline. The two-track strategy. Here is what actually makes China's position notable, and it is not any single machine. China is the only country running two distinct quantum architectures at world record level simultaneously. On the photonic track, you have Jiuzhang, which we have just walked through. On the superconducting track, the same institution runs the Zuchongzhi line. Zuchongzhi 3.0, announced in 2025, uses 105 readable qubits and 182 couplers, and posted random circuit sampling results competitive with Google's best. A commercial version has since been connected to a public cloud platform that has drawn tens of millions of visits from users in more than 60 countries. Two completely different physical approaches, both at the frontier, both funded, both staffed, both producing results in top journals. That is a hedge. Nobody currently knows which physical architecture will win the road to a genuinely useful, error-corrected quantum computer. It could be superconducting circuits, it could be photonics, it could be trapped ions or neutral atoms, where other groups lead. Betting on one and being wrong costs you a decade. If this pattern sounds familiar, it should. It is the same structural logic that shows up across Chinese industrial strategy again and again. Pursue several paths at once, accept the inefficiency, and make sure that whichever one turns out to matter, you are already standing on it. And there is a second piece that gets even less attention than the hardware. In February of 2026, Origin Quantum released an operating system for quantum computers as a free public download, capable of managing superconducting, trapped ion, and neutral atom hardware. Free, downloadable, and designed to be adopted by anyone building a quantum machine anywhere in the world. That is not a hardware play. That is a standards play. It is the same strategic instinct behind releasing powerful AI models as open weights. You may not win by owning the best machine. You can win by owning the layer everyone else builds on top of. What to watch? If you want to follow this properly rather than reacting to the next round of headlines, watch 3 things. The first is error correction, not qubit counts. Qubit counts are the easiest number to inflate and the least informative. The real milestone is what physicists call surface code distance, which is a measure of how much noise a logical qubit can absorb before it fails. The Zuchongzhi team has stated it is working through distance 7, aiming for 9, and then 11. If those results land and scale as predicted, that is the signal that fault-tolerant quantum computing is genuinely approaching. That will not be a flashy headline. It will matter more than any of them. The second is whether the classical side punches back. Watch for tensor network papers targeting Gaussian boson sampling specifically. If the Jiuzhang 4.0 result survives 3 or 4 years of serious classical assault, its standing goes up enormously. If it falls, that tells you something too. The third is adoption of that operating system. Software standards are quiet, boring, and they decide who controls an industry for 30 years. Step back. So what really happened here? A team in Hefei spent years fighting a war against photon loss, one component at a time, and eventually pushed a system of extraordinary complexity past the 50% efficiency threshold. That let them detect 3,050 particles of light in a single coherent quantum state, more than 10 times what anyone had managed before, and use it to answer a question that a classical supercomputer could not answer in a span of time longer than the universe has existed by an unimaginable margin. The question was chosen to be unanswerable. That is a fair criticism, and it is not a small one. But the machine that answers it is real. The photon losses that were supposed to make it impossible were beaten with actual engineering. And the country that built it is running the same play on 2 separate architectures at once, while quietly giving away the software layer underneath. None of this means quantum computers are about to change your life. That remains years away, and anyone giving you a confident date is guessing. What it means is narrower and more concrete. The list of countries capable of operating at the absolute frontier of this technology is very short. It has 2 names on it. And on this particular branch of the tree, on this particular week, the machine that went furthest was not built in California. If this gave you a clearer picture of where quantum computing actually stands, hit that like button, subscribe, and turn on notifications, because we take stories like this apart every single week. And here is the question for the comments. Given that these machines are still solving problems chosen specifically to make them look good, do you think quantum computing is the most important technology of the century, or the most overhyped one? Tell me which, and tell me why.